Ever lose, like, one contact lens? It's the worst, Rev. You're practically blind in one eye, on your hands and knees. It's like trying to find a sequin in a stadium after a rock concert.
Ouch, I can just picture it.
And as frustrating as that is, particle physicists deal with a similar headache. Except they're sifting through the remnants of, get this, billions of particle collisions.
Try and find the ones that could rewrite the physics textbooks.
Exactly. It's like finding, I don't know, a needle in a haystack the size of a small planet. Talk about a cosmic case of where they put that.
And just like your eyes might glaze over scanning that stadium floor, even the most powerful computers we have, they start to sweat when faced with that kind of data deluge from particle colliders.
Which is where our friend quantum computing strolls in, promising to be the metal detector this field so desperately needs.
It's not just about speed, though, although that's obviously a huge factor. It's the potential to unlock entirely new ways of analyzing information.
Okay, now you've got my attention.
To use your analogy, what if instead of painstakingly searching for that single needle, we could analyze the entire haystack's composition all at once?
All right, color me intrigued. But before we get too far ahead of ourselves, let's bring our listener up to speed a bit. We're focusing on a process called charge track finding. And don't worry, you don't need a PhD in physics to follow along.
No, absolutely not.
What's the elevator pitch, the gist of it?
Okay, so picture this. A cosmic game of billiards. Each collision sends these particles scattering in every direction.
Okay, I'm picturing it.
And these particles, they leave trails. Think of them like little subatomic breadcrumbs in the detectors surrounding the collision point.
Subatomic breadcrumbs, I like it.
So charge track finding is basically reconstructing the path of each crumb. Where did it come from? What kind of particle did it belong to? It's a bit like cosmic detective work.
So kind of like a cosmic CSI team, right? Piecing together the story of a collision, one subatomic breadcrumb at a time.
Precisely. Now imagine the challenge when you have not just one collision, but billions of these things happening every second.
My brain hurts.
That's the reality physicists are grappling with.
It's like trying to follow a conversation in a room full of people talking at once. No wonder they need a quantum assist. And that's where this paper we're diving into comes in. It suggests something called this quantum template matching technique. Honestly, it sounds more like a sci-fi movie title than actual science.
Perhaps, but it's rooted in some very real and very exciting physics. So imagine, instead of testing every possible particle pass one by one, you have this set of stencils. Each one represents a different path. Quantum computing lets you, in essence, try all those stencils simultaneously.
So it's like having a universal key, unlocks every door instantly.
Exactly.
Okay, now you're just showing off how fast these quantum computers are.
Mhm.
But seriously, walk us through how this whole trying everything at once thing actually works, the superposition thing. I think that's where things get really mind-bending for me.
It is. It's the heart of what makes quantum computing so powerful. It's about embracing uncertainty, in a way.
Okay.
Think of it like this. Imagine a single particle, right? But it exists in multiple possible states all at the same time, like it's traveling down every possible path simultaneously. That's the power of superposition.
Okay, I think I'm sort of wrapping my head around this whole superposition thing, but how does this quantum stencil matching, as you called it, actually work in practice? It can't just be a free-for-all of particles just flitting about, can it?
Definitely not. It's much more, well, choreographed. Think of it like a dance, a very, very precise dance. The researchers behind this paper, they figured out this really ingenious way to encode the information from the detectors.
The information about the particle hits.
Exactly, onto these quantum states, these superpositions we're talking about. And then by, carefully manipulating these qubits, they can basically ask the quantum computer which one of these stencils, these possible particle paths, best matches the data we've got. Amazing.
So it's not just about the qubits being in multiple states at once. It's about how they use those states to pinpoint the right answer.
Exactly. It's like, how can I explain this? Imagine you have this giant combination lock, right?
Okay, I'm with you.
And each possible particle path is like a different combination. Now, a classical computer would have to try each combination one by one, which takes forever. But a quantum computer, with this template matching, it's like trying all the combinations at the same time.
And boom, finds the right one. Much faster.
Exactly. Orders of magnitude faster, potentially. But of course, there's a catch. There's always a catch.
Oh, I don't like the sound of that. What's the catch?
Well, in the real world, detectors, they aren't perfect. sometimes they miss things.
Right, those cosmic breadcrumbs we were talking about.
Yeah, sometimes those breadcrumbs, they're smudged or maybe even missing altogether, and that can really throw a wrench in the system.
Makes sense.
Yeah.
So how do they deal with that?
Well, that's where the real beauty of this quantum approach comes in. It's incredibly adaptable.
Adaptable how?
Let's go back to our detective analogy for a second. Imagine you're at a crime scene, right? And you find a partial fingerprint. A classical algorithm might just hit a dead end there.
Not enough information.
Right. But this quantum algorithm, it can actually analyze all the possible particle paths, even with missing data. It's like it's saying, okay, we're missing some information here, but based on what we do know, these are the most likely scenarios. Pretty cool, right?
That's amazing.
Wow.
It's like having a detective who can solve a case with only half the clues. I bet a regular computer couldn't pull that off.
You're right. Classical algorithms, they really struggle with missing or noisy data. But this adaptability, this flexibility, it's a complete game changer, especially as detectors become more complex and the amount of data we're dealing with just explodes.
I can imagine. But let's bring it back down to earth for a moment. Why should our listeners, who might not be, particle physics aficionados, care about finding these particle tracks faster? What's the big deal?
That's a great question. And it gets to the heart of why this research is so exciting. It's not just about making calculations faster, it's about what those faster calculations allow us to do.
Which is?
Discover. Faster, more efficient track finding could lead to the discovery of new particles, new forces, even new physics that could completely change how we understand the universe. And it's not just about finding things we already know are out there.
It's about the stuff we don't even know to look for yet. The unknown unknowns.
Exactly. And being able to do it all in a fraction of the time it would take with our current methods. It's like hitting fast forward on scientific discovery. And not just in particle physics, but potentially in other fields too. Medicine, materials science, you name it. The possibilities are pretty mind-blowing.
Yeah, it's like we're not just trying to solve a puzzle, we're trying to figure out what the puzzle pieces are in the first place.
Exactly. And this research, it's showing us just how powerful those tools can be.
It's kind of mind-blowing when you think about it. This thing, quantum mechanics, it seems so abstract, so out there. Yet here it is, potentially revolutionizing how we understand the universe.
And we're really just scratching the surface here. The paper we've been discussing, it focuses on this very specific problem, charge track finding, but the potential applications of quantum computing in particle physics. I mean, forget particle physics, in all of science. The sky's the limit.
It really feels like we've stumbled upon like a secret room full of mysteries,
Yeah.
and we're just starting to peek inside.
And who knows what we'll find in there? It could change everything.
Well, on that note, I think it's time to wrap up this deep dive. But before we go, I want to leave you with something to think about. Imagine you had access to a quantum computer. Not just any computer, but a machine capable of tackling the most complex problems the universe has to offer. What would you ask it to solve? It's a question worth pondering as we enter this new era of discovery, an era where the line between science fiction and reality seems to blur a little more every day. Who knows, maybe one of you listening will be the one to program that quantum computer to finally unlock those secrets. Until next time, keep exploring.